All right, so section 8.7 is, again, approximating integration. Now, we know integration is area under the curve, and we learned back in section 5.2 several different ways to approximate area under the curve. We used left endpoints, we used right endpoints, and we used midpoints. So the idea there that if we used left endpoints, we were taking our region and dividing it into subintervals. Sometimes they would tell me use 4, sometimes they would tell me use 8. We even had a program that we used, that new Mint program, that we could go in and play around with it, and we could tell it use 10 rectangles, use 20, use 50, use 100. And it was back when we were exploring the idea of the definition of a definite integral. And we eventually found out that a definite integral was the limit as n approached infinity of that summation, where n was the number of subintervals. So we found out that basically if we're looking at these diagrams with the left and the right, the more rectangles that we made, the better the approximation was, until it eventually led us to, if there were an infinite number of these, we would have the precise area under the curve. But when we were approximating with a limited number of subintervals, we could use either left endpoints, where we took this first subinterval and we said, okay, if we're going from this piece to this piece, I could use the left-hand side to set the height of my rectangle, or on that same interval, I could use the right-hand side to set the height. Because this was an increasing function, the left-hand endpoint gave me an underestimate because I had this excess space in here that wasn't being calculated. The right-hand endpoint gave me an overestimate because I had this excess up here that I was including that shouldn't be there. And so one of the best alternatives that we found was, instead of using left or right, we could use a midpoint. So if we took that same subinterval and we took the middle of that interval, so maybe I was integrating this subinterval right here, maybe was from 0 to 1, and so I would take the midpoint, which was 1/2, and I would use that to set the height of that bar. When I did that, I would have a little bit of overhang and a little bit of underhang that pretty much balanced each other out, and that gave us our best approximation. But honestly, if we were to isolate one of those subintervals and actually look at the figure that is underneath the curve, does that not look like a trapezoid? And I know how to calculate the area of a trapezoid. So instead of going through and summing up the areas of rectangles, why not go through and sum up the areas of trapezoids? And that's exactly what trapezoidal rule does. Now, let's think about the area of a trapezoid for just a second. Area of a trapezoid is going to be 1/2 base 1 plus base 2 times the height. Now, the bases are the two parallel sides. So we're talking about this would be one base and this would be one base, and then this is going to be my height because it's going to be perpendicular. So if I'm looking at this in light of area under the curve, my height is going to be the change in x, and my base is just going to be the y value that's associated with whatever x value that I'm working with. So I could go through and I could say, okay, 1/2 base 1 plus base 2 times the height. For that first trapezoid right there, I would do 1/2 the height, and the height would be the change in x. Base 1 would be this first side right here, and so that would just be the y value that's associated with my starting point, x sub 0. And base 2 would be this guy right here, and that would just be the y value associated with the endpoint of that first subinterval, x sub 1. All right, then when I go to find the area of this second trapezoid right here, it'd be the same idea, 1/2 change in x, but when I go to use base 1 and base 2, notice that base 1 is going to be that same side I just used in the first trapezoid, right? So what is base 2 in the first trapezoid will be base 1 in the second trapezoid. So when they share a side, it's going to get used twice. And then I could keep going with that same idea. So I could go through and say, here's the area of the first trapezoid plus the area of the second one, and keep going until I got to the last one. So that helps us understand where they come up with the trapezoidal rule that you see on page 547. They say trapezoidal rule is just going to be change in x divided by 2. Okay, that's 1/2 change in x. That's what we had in front of every single one of these. Then we're going to multiply it by f of x sub 0 plus 2 times f of x sub 1, 2 times f of x sub 2, all the way through until I get to the last one, and it's just a plain f of x sub n. So everything is a multiple of 2 except for the first term and the last term. Why? Well, because in this first trapezoid, this is not a shared side, right? So it only is base 1 for the first trapezoid, and it's not used for anything else. As we already mentioned, this is base 2 for the first trapezoid and base 1 for the second trapezoid. Because it was a shared side, it got used twice. So when I get down to my last interval down here, this last leg where my interval ends, x sub n, isn't going to be a shared side. So it's only going to be base 2 for one of the trapezoids. That's why the first one and the last one don't get doubled, but every other value does. So yes, we can just go through and memorize this formula, but I wanted you to see where it came from because it's very logical as to what we're utilizing here. Okay, so let's look at example number 1. Example number 1 says, use the trapezoidal rule, and let's go back and review and use the midpoint rule as well, with n equals 5 to approximate the integration of 1 over x from 1 to 2. Now, I'm going to change this problem just slightly, because I would like for us to use the exact same example for trapezoidal, midpoint, and something else that we're going to learn today, Simpsons, because I want us to be able to compare our answers and see which are the best approximations. When I use Simpsons, I can only use an even number of subintervals. So I'm going to alter example number 1 in our book to be 6 subintervals. So when you look back at this later on, there's going to be a difference for that reason, so don't let that confuse you. Okay, so if we have n is equal to 6, change in x is going to be the same as it has been all the way back to chapter 5. Change in x is just going to be b minus a over n. So this is my lower limit of integration. That's my starting point a. Upper limit of integration, my stopping point b. So b minus a over n gives me a change in x of 1/6. My starting point, again, as we said, is 1. That's x sub 0. And if I add that change in x, then right here I'm going to have 1 and 1/6. Probably a little bit easier to write that as an improper fraction, so I'm going to write it as 7/6. Add 1/6 to that, and I'll have 8/6. Add 1/6, 9/6. Add 1/6, 10/6. 11/6, all the way to 2. You could also reduce those if you wanted to. All right, so now let's follow our formula. Our formula says, now that we've identified these values, we're going to take the change in x and divide it by 2. That's the same thing as change in x times 1/2. So our change in x was 1/6, so we can say 1/2 times 1/6. Now we need f of x sub 0, and we identified x sub 0 as 1. And then we'll do 2 times f of x sub 1, so that would be 2 times f of x sub 1, 2 times f of x sub 2, x sub 3, x sub 4, x sub 5, and only 1 times x sub 6. So basically my a and b values, my starting and stopping points, do not get the value doubled. Once I plug them into the function, everything else does. Now for this particular function, I've got 1 over x. So when I plug each of these values into the function, I'm just going to get the reciprocal, right? So we could go through then and we could say 1/2 times 1/6 is 1/12. And so when I plug 1 in, I'm going to get 1. Plug in 7/6, then I'll get 6/7, 4/3. Flipped is 3/4. Reciprocal of 3/2, 2/3. 5/3 becomes 3/5. 11/6 becomes 6/11, and 2 becomes 1/2. I'm definitely going to want at least a scientific calculator to help me do that type of computation, right? So even if I don't have my graphing, I'll want to be sure that I utilize my scientific, or I'm going to be doing fractions for a good long while. Not that we can't do that, but that's not really our focus at this point. So there's the approximation that we get for our area under the curve using the trapezoidal rule. And in theory, it looks like it should be a really good approximation. I mean, it's a great fit for the figure that we have under the curve. So let's go back. When we did left, right, and mid, the best approximation that we had was mid. So let's try that and see how midpoint and trapezoidal compare to each other. So remember that when we did the midpoint rule, we would go through and for each of our intervals, we would find the mean of that interval. So for instance, the first one went from 1 to 7/6. So if I'm looking at the interval from 1 to 7/6, I could say 1 plus 7/6 divided by 2, and I'd get 13/12. Or maybe you'd rather rewrite each of these with a denominator of 12. If I do that, 1 is 12 twelfths and 7/6 is 14 twelfths. Then it's really easy to see halfway in between those is 13 twelfths. And once I establish the first one, it's easy to move forward because the change in x is still 1/6, right? 2 twelfths. So I could just go through and say, okay, let me add 2 twelfths here. That'd be 15 twelfths. Let me add 2 twelfths. That'd be 17, 19, 21, 23. So you don't actually have to calculate the mean for every single interval once we get started. So again, just for review of our midpoint rule, it is going to be the change in x, which is 1/6. And then we're going to go through and plug each of the midpoint values into the function. It doesn't get multiplied by anything or anything like that. And again, because our function was 1 over x, then I would just get the reciprocals of each of those when I plug them into the function. I could do some tedious fraction work, but again, since that's not our focus, I'm going to put that into my calculator and I'll get an approximation using 6 subintervals and midpoint rule. Now you might remember back in section 5.2 when we would do this by like left endpoints and right endpoints and midpoints and we would compare them. Left endpoint and right endpoint might be, 6 whole numbers different from each other. But look, if you would, at the two approximations that we got. We have 0.694 and 0.692. They're only 2 1,000ths different from each other. Gives us a pretty good idea that both of those must be close approximations to what I'm trying to get. There is one other way that they show us in section 8.7 that we can approximate the area under the curve, and that's on the bottom of page 550, and that's with something called Simpson's rule. It's actually Simpson's parabolic rule because it's based on the ideas of parabolas. If I'm trying to approximate the area under the curve and I look at the most natural shape that I have here, even if I'm working with a trapezoid, that's a great approximation, but if I blow this figure up, a trapezoid has a straight edge and a curve does not. So I'm still going to have a gap there. Why not use a curve then? We've not tried that. Everything that we've used has been a straight edge, a rectangle or a trapezoid. And so Simpson's parabolic rule says, since it has a curved shape, why not use parabolas to approximate? And so that's what they show you there on the bottom of page 550. Now again, it's not perfect. You'll see that there's overhang and underhang, and so it's going to still be an approximation, but Simpson's is a great approximation. So here's what Simpson's rule says, and they give us Simpson's rule on the top of page 552. Simpson's rule is going to be the change in x divided by 3, f of x sub 0 and f of x sub n, my upper and lower limits of integration, my starting and stopping points, are going to not be multiplied by anything, but every other number in between, when I plug it into the function, I'm going to do a multiple of that value that I get, just like I just did with trapezoidal. However, with Simpson's, it's not going to be 2 times everything. It's going to flip-flop. It's going to start with 4, so I'll have a multiple of 4, and then a multiple of 2, multiple of 4, multiple of 2, and it'll keep right on going. All right? So the first term and the last term, I just plug into the function. I don't do a multiple of it at all. Every other term in between, I start with 4, and I alternate back and forth, 4, 2, 4, 2, 4, 2. All right, so let's take this exact same problem that we've been working with, and let's see what we get if we do Simpson's. So again, I start with my formula. It's the change in x divided by 3. That'd be the same thing as change in x times 1/3. Then it says plug in x sub 0, and higher up on your page there, we've already identified what each of those values are. So x sub 0 was 1, x sub 1 was 7/6, 8/6 that we reduced to 4/3, 9/6 reduced, 10/6 reduced, 11/6, 12/6 reduced. So those same values that we plugged in earlier for trapezoidal. Again, because our function is 1 over x, we're going to give the reciprocal of each of these values. I wouldn't do that in every function. If my function was x squared, I'd be squaring every one of these values. It's just the example that we're using. And then again, I can throw that into my calculator to get my approximation for the area under the curve. Now, our calculator can tell us the exact area under the curve, accurate to about 8 decimal places. That means that it's still an approximation if it doesn't give me the exact fractional value, but according to my calculator, the area under the curve is 0.6931471,806. So let's look at those 3 calculations that we just did, the 3 different methods for approximating. We took the best thing that we had learned earlier this year, and now we're pairing it with 2 new methods that we've picked up today. So let's see how they did. For this first one, you'll notice I've got 0.6931. Down here I've got 0.6948. So if we're looking at the difference between 31 and 48, to only be off by 17 ten-thousandths, that's pretty good, right? All right. How about midpoint, our old faithful that we used? If you look at this one, 6922, 6931, if I compare 22 and 31, we're only off by 9 ten-thousandths. But look at Simpson's. 0.69316 is where we have to go before we hit the first discrepancy, 0.69316. We are only off by 2 100,000ths, right? That's crazy. So Simpson's is a great approximation. The other 2 are very good as well, but Simpson's is probably the best that we've found. Okay, so I had asked you to link Simpson's from my calculator. So let me show you how you can do that on the calculator, and then I also want to go back and remind you of something that we knew how to do back in Chapter 5. We want to be sure that we still remember how to do today. Okay, so here's how Simpson's program is going to work, the one that you just linked. You may need to unarchive it. So remember, to unarchive, you're going to go to second plus sign, which is memory management. Thank you. Go down to number 2, memory management, delete. You can either choose all or you can scroll down to programs, either one. Anything that has a star by it is archived. When you hit enter, the star goes away, it's unarchived. Anything that doesn't have a star by it, when you hit enter, the star comes back, and now that means it's archived. So you can archive and unarchive multiple things at one time in that way. And then you want a second quit to get out of that. So if you've linked it and it's archived, that's how you can get it unarchived. All right. You want to tell your calculator what equation that it's using. So let's go to y equals, and let's put in the equation that we were using today, 1 over x. Then I'm going to go to my programs, and I'm going to run Simpson's. You've probably got a bunch in there by now. You can do alpha S to get it to jump down, just like you're going to do on your cell phone for your contacts. All right, so I'm going to choose Simpson's, and when it comes up, it's going to give me these prompts. It's going to say, what's n? N was the number of subintervals that we used. We used 6, right? So hit 6, enter. And then it's going to ask you for A and B, your upper and lower limits of integration, or the endpoints of your closed interval, depending on how the problem is posed to you. So A is going to be 1 and B is going to be 2. And in a fraction of a second, it does the exact same thing that we did up here. You'll notice exact same answer. That's S6 right there. So doing something like this, if you think about it on the AP exam, there is no scientific calculator option, right? It's either with a graphing calculator or without. We absolutely could do something like this without a graphing calculator, but it's going to be pushing it to do it in a minute and a half or 2 minutes, which is kind of the time constraint that I'm looking at. So if they were going to ask me to do Simpson's and they were going to give me a graphing calculator, then I might as well utilize the program, unless they just asked me to give a setup or something like that. Now, what we had used back in Chapter 5 was the NUM-INT program. This is the one we were referring to earlier, where we would get it to approximate if we had multiple subintervals, like maybe we would use 10 and then 20 and then 50 and then 100, and we could actually see it calculating the area under the curve and that getting closer and closer and closer to a precise value. So the way that we did that was, again, we had to put our equation in y equals. I set my window because I'm really only interested in looking at this from 1 to 2, and I wanted a close-up image of that. I set my window to go from 0 to 3 counting by 1, but you could set it to whatever you wanted to. I'm going to run my NumInt program, and when I do, it asks me for those same upper and lower limits, my A and B values. And then it asks me which method do I want to use. Now, we had used left, right, and mid before, but we had not seen trapezoidal before, right? It's been there in the program. We just didn't have section 8.7 yet. So now I can choose trapezoidal, and it's going to ask me how many subintervals, and I'll tell it 6. And so it gives me this pretty little picture here where it's showing me how it could subdivide that and calculate that area under the curve. And remember, the little dancing dots up here mean that it's paused, and if you hit enter, it will go on and do something else for you. So when I hit enter, it actually tells me what that area is, and you'll notice that is the exact same answer that we got when we did T6 higher up on the page. Then you'll notice it's prompting me, do you have another number of subintervals that you want me to calculate? So if they had said do this for 6 and do this for 12, and I could go ahead and do that. Remember that if I want to get out of it, I just say 0 right there, and that's how I get back to my menu. This time I want to choose midpoint, since we also worked this problem by midpoint. And so again, it would ask me for the number of subintervals, and it would show me the graph, and I would hit enter to get it to give me the area, and that's the answer that we got earlier today when we did M6, and that's the same way we did that back in chapter 5. So just wanted to go back through that with you to make sure that you remembered how to use those tools. Now, for our homework tonight, we're only doing 2 of these. I know they're time consuming. We are doing these by hand. We are not using Simpsons or NumInt. We're doing them by hand. But please check your work with those programs. I need to make sure that you remember how to use NumInt and you understand how to use Simpsons so that we can utilize those. Okay?